Hello. Today we're going to begin talking about applying tangents. And there's a few vocabulary words that we'll have to first introduce to make sure you understand exactly how that happens. But to begin with, we just have to make sure we understand that tangent is going to be the opposite over the adjacent. And so those scenarios come up fairly often in regular real-world problems. And we want to make sure that you're understanding of how to potentially use this. So potential vocabulary you're going to use is right triangle, sine of an angle, cosine of an angle, tangent of an angle, opposite side, adjacent side, hypotenuse, angle of elevation, angle of depression. And those two are the newer words that you're encountering today. Again, it becomes very important that you understand and you can label the opposite side and the adjacent side as you start looking at these real-world problems. Okay? And so as you're looking at this diagram, you can see two people, one at the bottom of the steps and one at the top of the steps. The only thing that they have in common is that they have a horizontal from their viewpoint. So there is a horizontal line, which means a line that goes directly across like a horizon. And from that, we get two different angle definitions. One being the angle of depression, and depression really just means going down. So you're looking at this is going down. And the other one is angle of elevation, which just means elevation going up. Okay? And so these two vocabulary words oftentimes get confused. Especially the angle of depression. A lot of people don't understand exactly how this is put together. And so again, I want to make sure we understand that an angle of elevation and angle of depression is an angle from the horizontal. This is really key. From the horizontal, either down for depression or up for elevation. Now what's really nice is the horizontals are parallel lines. So this horizontal and the other horizontal, they're parallel lines. Parallel lines cut by a transversal. And we should know by now that if parallel lines are cut by a transversal, alternate interior angles are equal. And so that helps kind of prevent mathematical errors, but we really do need to ensure that you guys understand those two definitions. Okay? So here's one example. Standing on the gallery of a lighthouse deck at the top of the lighthouse, a person spots a ship at an angle of depression of 20 degrees. Well, how does that get set up? You take from the lighthouse and you make your horizontal. And then the angle of depression down to the ship. Now, these are not exact word problems. They really should give you a little bit more idea as to whether you're talking the top of the ship, the bottom of the ship, where the water hits the ship, etc. But let's just go with what they did give us, and the angle of depression. So here's my horizontal. And I'm going down from it because it's the angle of depression, 20 degrees. Please make sure you understand exactly where that 20 degrees goes. And then if we were talking the height of all of this, okay, we'd be making this down. The lighthouse is 28 meters tall, and the cliff sits on a wall 45 degrees. So realistically, I should have put this down to the water. All right, so you just got to read the problem very carefully. And so what I now have is this right triangle. Okay, my right angle is up in this corner. And as I calculate through this total distance right here, will be the sum of 28 plus 45. Okay, which is equal to 73. And so my setup depends on me making sure that I'm very comfortable talking about my opposite. So here's my opposite, here's my adjacent, this is my hypotenuse. And they want to know what is the horizontal distance between the lighthouse and the ship. So really what they're asking me is what is the adjacent distance with the opposite, because they gave me the 73. And if I know my SOHCAHTOA, I know that that's tan, so tan of 20 degrees is equal to the opposite. Always write these formulas out over the adjacent, so tan 20 degrees equals opposite, which is 73. The adjacent is what I'm looking for, it's my unknown. I can use my calculator to get the tan of 20 degrees, which is 0.3640. 73 over x. Then you can multiply both sides by x. So 3640x equals 73. Divide by 360. Divide by 3640. And x is equal to, again, calculator, 200.55 meters, which is approximately 201 meters. So the distance between these is 201 meters. Okay, so again, sometimes these realistic problems, they make a few assumptions. This one was that the boat hit at the actual point on the water. But in general, this is the setup. Okay, now there's a second thing you can sort of view this as is on a coordinate grid. And if you're looking at this picture right here, you just need a horizontal. It doesn't really ultimately matter where that is. And what's nice about these is angle of elevation starts from that horizontal and works up. If you memorize that definition, is you can calculate the slope of the line. Okay, because this is your opposite, this is your adjacent, but if you think about this, this is your change in y, and this is your change in x. And so if I think about slope as equaling the change in y over the change in x, okay, now these are nice numbers, but there will come a time when they're not very nice, and this is the point that tangent can be helpful. And so if I look at this, this is a change in slope of x over and y. So change in y was 4, change in x is 8. And so the slope is 4 over 8. But I could also have said the tangent of whatever angle this is, and then given you the decimal number. This one just happens to be nice, and 0.5. Likewise, if you're talking about angle of depression, notice I'm going down from my horizon, and they don't actually give me the values. And so this is why tangent could be really helpful, because I don't know exactly where this is. It looks like it kind of hits right there, but if we zoomed in really, really close, we'd notice it wasn't directly through that. So if they knew the angle, I'd be able to get a decimal for the slope. And that's exactly what we're going to do in this next example. It says on the coordinate grid, the angle of depression is 36 degrees. Find the slope. A few things here. The tangent of theta will only give you the absolute value of that slope. You have to make sure you understand whether it's going down or up. If I drew the picture in a different orientation, if I had something like this and I was asking for the depression, well, that slope is going to be positive, right? Because they could also look at it from this direction on. So you have to be very, very careful as you're going through this. The tangent will only give you the absolute value of the slope, but tangent of 36, and again, we get to do this because the tangent would be the opposite over the adjacent. Tangent of 36 degrees gives me m over and this ratio. If you use your calculator, though, you'll get tangent of 36 as 0.7265, and that's the decimal equivalent or approximation of my ratio of the opposite over the adjacent, or the change in y over the change in x. And now, because this is negative, I know the slope must be negative 0.7265. Okay, so that's one awesome use of the tangent ratio in a realistic sense, is if I know the angle, then I can figure the rest out. The final problem we're going to look at today is one of these triangles. And the question is, how long is this segment? Ultimately, this is what I want to know. This length, call it x. Okay. And right now I look at it and I'm very tempted to use Pythagorean theorem because I have two side lengths, but then I look very carefully and I recognize that this does not say 90 degrees, and we are only allowed to use Pythagorean theorem if we have a right triangle, and therefore we cannot. All right, so then I'm stuck. I can't use Pythagorean theorem, but what I can do is I can draw an altitude. So now I do have a 90-degree angle here. The question is, how did this triangle split up? Well, if this bottom angle is 50, that would mean that this is 40 degrees. And if this is 35, that means this is 55 degrees. And 55 plus 40 is 95. So it all checks out. And then what I kind of have is the desire to know this distance right here in purple and the distance in blue. And then that would give me how long my x is if I added those two segments up. And so if I'm looking at this, I could say, well, I have the opposite of 55 degrees. This would be my adjacent. I have the opposite of 40 degrees. And so I could use sine. Or even cosine, depending on how I view this. So I set it up. I said cosine of 35 degrees, which we know if they're complementary angles, that's the same thing as sine of 55 degrees. So it's that purple equals the purple line, the purple unknown. And just for convenience sake, I'm going to use y over 100. And these two decimals are equivalent, so 0.8192. Notice I'm going out 4 decimal places. The y value over 100. So probably should make sure that we label that y. Multiply both sides by 100. And I get 81.92 is equal to my y value. The other side of this would be sine of 40 degrees is equal to the cosine of 50 degrees. We'll use z, so it's the blue, which is z over the hypotenuse, which is 74.875. These two are equivalent, and they equal 6428, which is z over 74.875 multiplied by 74.875 on this side, multiplied by 74.875 on the other side, golden rule of algebra, and I get 48.1297. It's approximately equal to z. Now the question wanted to know what's the total length of these two things, so I have to make sure I add those two numbers up, and I get 130.0497. All right. So that's an application of tangent. It sort of builds on some of the application problems you've seen for sine. and cosine. Make sure you truly understand the difference between angle of elevation and angle of depression. It's a very common thing for students to look at the angle of depression and put it here against the wall and then the line of sight down. Remember, it's always from a horizontal. It's got to be from a horizontal and then down. So thank you for your time.